left off. All right, so now we're going to get into how do we use this Newton's law of gravitation to solve for things like orbital speed or gravitational acceleration? Because earlier we said it's not always 9.8. What if it's different? So that's what we're going to do first here. Derive an expression. So this is all just going to be variables for little g. And remember, little g is an acceleration due to gravity. Sometimes we just call it g, but it's an acceleration still. So solve for acceleration using the law of universal gravitate. We kind of already did that, right? So in the back of your mind, think about that example. Here's our Earth. There's our satellite. It's orbiting. And so for the satellite, our small mass, the only force acting on it is F big G. If you want to draw it in your picture, you can. Well, F net equals which mass? Mass 1, whatever small. Here I went with satellite, right? But use your subscripts or case sensitivity. I'm not always case sensitive. And so that's why I like the subscripts. And what kind of acceleration is this? Well, here it's an acceleration due to gravity. Equals our new equation, big G, little m satellite. In my example, what would be the big mass? Earth. So I can put mass 2, mass big, however you want to do it. I'm just making it unique here. All over r squared. And again, r is the radius of the Earth, but it's in addition to that, it's that full radius of the orbit. It's that center to center distance separation. Well, just like we saw last time, mass satellite cancels. And so this is our derived equation for AG, which is the gravitational acceleration. And it's equal to big G, big M, here mine is Earth, over r squared. Now that one's not on the formula chart, but isn't it pretty easy to get? I mean, Newton's second law and the universal gravitation equation is on the formula chart. So hopefully you can deduce it easily if asked to do so. Notice, does the acceleration of gravity depend on the object itself? Kind of, sort of, not the mass, but it does depend where it is, right? And so the closer it is to Earth, the acceleration will be higher or lower? Greater. And the further your object is from Earth, the acceleration due to gravity will be smaller. So as things go further from Earth, gravity 9.8 decreases. Okay. Well, what if we're not orbiting? So here's another way where it's not always necessarily equal to r. What if I'm just standing on the Earth? And to make it a little more interesting, let's go stand on Mount Everest. And we won't talk about, cold temperatures or lack of oxygen. We're just focused on the gravitational acceleration at the top of Mount Everest. Again, you don't have to memorize this number. It's given. And so it's 8,848 meters above the Earth's surface. And so if you want to draw a little picture, here's our Earth, there's the center point. Maybe here's our Mount Everest, and we're at the top of Mount Everest, right? And so what distance separates the centers? Now, true story, my radius, 1 meter, insignificant to the 8,000. Insignificant to the 6 million of that of Earth. Don't worry about my 1 meter above the Earth, the top of Mount Everest. Yes? So it's just this total. I'm not orbiting Earth, but it's a center to center separation. And so r would be the radius of the Earth plus whatever additional height above the surface of the Earth. And so previously, we said the radius of the Earth, 6 point, hold on, I always forget the decimals, 6.378 times 10 to the 6th plus that 8,848. And so it's not a huge change, but we're going to take it into account. We're going to take it into account. And I get 6.3869, right? So I'm going to keep enough, as much as I can handle. If you want to use the full number, that's fine too. Times 10 to the 6th. So when we go to use the equation, that's the center to center distance we'll use, not really a radius here. And so using our derived equation, g, little g, the acceleration due to gravity, is that big G, big M, not the mass of the person. Notice that's not given, divided by r squared. And so big G, 6.67 times 10 to negative 11. Mass of Earth, again, I want to get my decimals right, 5.972. 5.972 times 10 to the 24th. All over that 6.3869. Honestly, if we'd called that 7, that would have been just as good probably. But don't forget to square. And so let's work it out. So is gravity still going to be 9.8 at the top of Mount Everest? Well, let's see. Again, I like to break it up into numerator, denominator. Plus, it's a checkpoint for everybody. So my numerator, with as many decimals as I can stand. And then uh-oh. 8, 2, 3, 3. And if you've been calculating with me, maybe you now realize why most of your AP problems on May 12th won't involve a calculator. There's a lot of key punching. Say again?
He was asking how much less stuff up.
How it's, oh, okay.
The radius got bigger.
The radius got bigger. Numerator stayed the same. I'm almost there. Hopefully you did not get 9.8. 9.76. And as long as everybody is still SI, it comes out meters per second squared. Okay. And so you go up to Mount Everest, you're not going to be floating like it is on the moon, right? And so gravity is still gravity basically. Okay. But a little different. Now, and by the way, true story, we say 9.8, it's really 9.81. Significant? Not to our normal count. We round to 10 anyway, right? And so it's more about the physics. Here you go. Good there? All right, now you don't need a calculator for the next part, okay? These next two problems, they were tipper questions, which if we haven't said those words in a while, it's concepts. Okay, we'll do little qualitative math, but we're not going to need a calculator, okay? Both of these, what if you have 3 masses? I'm actually going to do the second one first because it's in a straight line and straight lines are easier, right? And then remind me, make sure we go back up and do the 2-dimension one. So here we have 3 asteroids. At the instant shown, they're all in a straight line. The distance between A and B is the same as the distance between B and C. And in the picture, they're both labeled D and D. Asteroids B and C have the same mass, 1m, 1m, but A has twice the mass. Rank the magnitude. Oh my gosh, it's April. What does magnitude mean? Size. Do we care about direction?
Yeah.
No, it's just how big, how small. The net force on each asteroid due to the other 2. Wait, what? Well, let's imagine we are asteroid A. Who are we going to have a gravitational force with? B? Yes or no? Yes. What about with C? Yes. There's going to be two gravitational forces on me, A. Okay. And so this whole thing on a particular asteroid, draw a free body diagram. So I'm going to try and break this area that I have up into 3 sections. And so, yes, net. They net with each other. And so the net force on A, well, let's figure out, let's draw a force diagram on A. So if we just look at A and B, that's an attractive force. But what direction is that force on A? A is getting pulled to the right. And so there's a rightward force on A due to B. Now, I just randomly assigned a magnitude. We actually should talk about how it's twice as massive, right? And so kind of on the side here, no, I think I can squeeze it in. FAB. So G is going to be the same for everybody. And again, we're not really doing calculator calculations. We're just doing proportions. So MA is a 2M, B is a 1M, and how far apart are they? 1D. Don't forget to square. So just looking at the 2 times 1 divided by 1 squared, we get a factor of 2. Okay. Then what about the force on A by C? So kind of ignore B for a second. Well, again, it's an attractive force. So what direction will it be? Also to the right, but how big is it? Is it the same size? Let's do that loose calculation first. So we still have G, same. Double mass, because that's A. C is also 1M, so it's got identical numerator. But now, how far apart are A and C? 2D, don't forget to square. So I end up with 2/4, which is what? 1/2. So it's a weaker force. And so in my diagram, I'm just going to try and draw it maybe 1/4 of the size. So the FAC is a much smaller force. Now they're both to the right, not that right matters. They're both the same direction. Isn't your net force going to be the tip to tail, from start to finish? It's an even bigger force. Good deal? If you want to call it 2.5, go for it for right now. Okay. Well, what about B? And so now the net force on B, again, we're going to be doing the qualitative math and then a diagram. Okay. Now B is in the middle. Can you understand why B is going to have a little tug of war going on? It's attracted to the asteroid on the left. It's attracted to the asteroid on the right. It's a little tug of war drama going on. And so let's figure out which one's bigger, because that one's going to determine the net force. And so FAB, isn't it the same? It's that same factor of 2, equal and opposite, but it's going to be to the right. So FAB is going to, oh, I'm sorry, to the left. I drew left. Thank you. But we have not calculated FBC. And so G is going to be the same. B has a mass factor of 1. So does C. How close are they? Well, 1D away. So 1 times 1 divided by 1 squared. It's what? It'll be a factor of 1, which is half of 2, right? And so maybe I draw this one half. Oh, what direction? Well, it's being pulled towards C, attracted towards C. So that one would be to the right. Now, it doesn't matter who's positive, who's negative. but your net resultant force on B will be more leftward, right? Or correct? It'll be to the left, a small amount. If you want to say 2 minus 1, it'll be 1 to the left. Where the other, A, we said it's like 2.5 to the right. All right, rinse and repeat. Now, the net force on C. Well, thankfully, we've already got AC and BC. And so A is going to pull it with a little arrow, 1/2, but this time to the left. So that's the half factor that we had previous. And then BC is a factor of 1. What direction? Also to the left, right? So C is on the rightmost point. It's going to be pulled to the left by both masses. And so this FBC, factor of 1. So overall, your net force is going to be to the left by a factor of 1.5. Again, loose math. Rank the magnitude. Forget direction. Look at value. Who has the greatest net force on each asteroid? A, B, or C? A, that 2.5 is bigger than C's 1.5, which is bigger than B's 1. Okay. Who would accelerate the most? Ooh, that's an even, right? Because they're not all equal mass. So that we could do that, but I don't have room. Everybody good with straight line net force? Now, what if we have some offset? Imagine these 3 asteroids, but now they tell us they each have the same mass. They're going to exert gravitational forces on each other. Which arrow shows the direction of the net force? Where's your preposition? On mass B. Who are we drawing a force diagram for? B. It's on who? So we'll draw a force diagram for B. Well, A and B are attracted to each other. What direction is that force on B? Just due to A. By the way, we're going to have identical mass, identical distances, 2 grids between A and B, 2 grids between B and C. And so this is more about direction, the magnitude. But A is going to pull on B to the left. And so we'll have a leftward force because of A. Now ignore A. What about B and C? Same mass, same distance. The force of B because of C is going to be what direction? It's attractive, so towards each other, but on B, it would be what specific direction? Down. The force between B and C. Now, yes, we could go ahead and put these same forces on A and C, but to answer the question that they're asking, I only care about the diagram of B. And so what is our final answer? Well, let's go back to basic vectors, y'all. A little bit of review of vectors. How do we add arrows? Tip to tail. So just a reminder, tip to tail. And so we have that left, we have that down. And where's our net force? Well, this is the resultant. How do we draw the resultants? Do we complete the cycle? Go back to the beginning? No, it's start to finish. And so your F net would be in the southwest direction. Answer choice 1, A, whatever. Good deal? And you could repeat this same thing, but change that on mass A, on mass C. And you'll have a diagonal in there, which makes it a little more challenging, but still doable. You'll know the distance between A and C is going to be bigger than 2 grid lines, right? So you could solve for it, right, if you wanted. No, thank you. I don't have a whole lot of room, so, and I want to move on, okay? But that would be a different answer. All right, the next 2 slides aren't really work, it's more like information. Did y'all know that satellites are falling? They're falling towards Earth. Now, how come they're not in our backyard here? That tangent velocity. They have enough speed to be in motion tangent to the circle, and gravity constantly is pulling on them to keep them in a circle, right? What if it speeds up too much? What if we miscalculate and we enter a speed greater than what we'll call orbital speed? Say goodbye. What if we miscalculate and the speed of that satellite is less than what it should be? Say hello, it's in your backyard, right? It's going to fall towards Earth. So even objects orbiting like the moon, the ISS, the astronauts inside the ISS, right? Now, let's talk about that for a second. I don't think it's on slides here, but we like to say that astronauts in the International Space Station, they're weightless. I mean, you watch the videos of them. Did y'all know they do experiments on the ISS? Physics, chemistry, biology. It's a one big lab. And so we say that they're weightless because they're like floaty, right? Is that true?
No.
Are they still under the effects of gravity? Yes, but not 9.8, right? And so they are falling inside of an International Space Station that's falling. And so just like if you were to get into a box and somehow fall through the air straight down, elevator, right? What if we were falling inside of an elevator when it was accelerating 9.8? Well, that net difference is nothing. It would be like you're weightless, right? And so are they really weightless? No. Is it because they don't have that support force to push back on them? Yeah, they lack a normal force up there because they're falling inside of a falling system. Good deal? Little different way of thinking of it. Okay, so satellites, they orbit by accelerating at high sufficient tangent speeds with the use of their rocket. So they can control it if they need to, I assume. I've never been in a rocket ship. I tell my son, don't leave Earth, so I better not leave Earth myself. Okay. Satellites are usually put into an orbit because they require the least takeoff speed. We'll compare it to something else in just a second. If it was too high, it would fly away if it left Earth's gravitational field. And so over here is the comparison. And so some of our satellites are put into orbit so that they have a circular orbit. And I guess I'm assuming this is an average, 27,000, now careful, kilometers, per hour. What about a different orbit? Well, we can have an elliptical orbit, okay? Now, by the way, we don't do the math behind ellipses. We're gonna assume circular orbits in here. And so, but if it's in an elliptical orbit, 30,000, a little higher, okay? And we'll talk about with conservation of angular momentum, that nearest distance and furthest distance of the elliptical orbit. But what if you launch it too quick? By the way, escape velocity is a launch speed. If you launch it from the surface of Earth at 40,000 kilometers per hour, what's going to happen to whatever you have in that ship? It's going to go bye-bye. Okay, so, hopefully NASA doesn't spend all this money on stuff and go bye-bye. Okay, but, play with me here. What if you don't like, Brussels sprouts? So you load all the Brussels sprouts in the world. Maybe you like them, I'm sorry. Take your least favorite food, substitute in. But what if you put them in a rocket ship, launch them at 40,000 or higher? Okay, you could do higher. Kind of that's a waste of fuel though. but you launch it into space. Literally, it leaves and never comes back. It escapes, it never comes back. It escapes our gravitational field, okay? And so it just it reaches the point where gravity says, okay, I won't pull you back in, okay? It's really far away, but it would take 40. So what does NASA need to know this number for? Maybe we want to be less than the escape speed, right? And so that's the limit. You don't want to approach that high speed. Good deal?
Kilometers per hour.
All right. Next page. This may be where we end. Let's see. Circular orbit. So again, we're not going to do the math behind the elliptical. Later, when we talk about angular momentum conservation, yeah, angular momentum, rotational kinetic energy still is in play with orbiting objects. But here, let's just focus on the circle. And so consider a small mass, little m. It's in a circular orbit with a radius r. And notice in the picture, that's going to be our center to center distance. And it tells us from the center of mass. And they stipulate that big M is much, much bigger than little m. In other words, little m is going to do the orbiting, big N is not. Determine an expression, variables, for the orbital speed v, and bring back the omega, angular speed for such an orbit. And they tell us, but hopefully we know by now that it's the gravitational force, big G, that provides the centripetal force. So again, if you want to draw your force diagram, just focus on the small mass. That's the one accelerating. And so F net for the satellite, or little m, I'll save it. We'll do little m, equals F big G. Break each of them down. We've already done this once. F net equals MA, which mass? The little m, and I'll try to be case sensitive. What kind of acceleration is this little mass experiencing? If it moves in a circle and gravity is center seeking, then it has centripetal acceleration. Yeah, it could still be an acceleration due to gravity, like we said before, but here we're going to take that centripetal acceleration approach. And then our new equation, F big G, is our big G constant times little m. I guess I should have just used little m and big M. Oh, well. Maybe I say m. Yeah, I don't know. Now I wish I'd done M1, M2. There we go. I know, I regret, but I'll go with it, right? Divided by that center to center distance squared, okay? And so what do we notice happens at this point? Small mass cancels, so goodbye, MM. Now, keep it going because we don't want an equation for A here. We've already done that. What if we want to put it in terms of V? Let's just do linear tangent speed first. And so it's been a while. What equation is on the formula chart, fifth or sixth one, for centripetal acceleration? V squared, and that's the tangent velocity, over R. And if I equate it to big G, big M over R squared, now what happens? The R on the left is literally a radius for the circular orbit. And then R on the right is that center to center separation distance, which is drawn and stipulated up above as being the radius. So R and R squared, what happens? One set of R's cancels out. So last step, solve for V. V would equal square root big G, big M over R. Everybody good? Okay. What about omega? And so omega, I'm going to refresh your memory from over a month ago. Y'all remember we did a lot of connection between simple harmonic motion, cyclic behavior, and circular behavior, yes? Remember, we did A max was equal to omega squared times the amplitude for cyclic, right? So whether it was springs or pendulums, we had derived this equation. Well, if cycles and circles relate, which now we know they do, how can I write this? Centripetal acceleration equals that angular acceleration. What would be our max amplitude, our max distance here in this problem? Don't think amplitude, just think about distance. R. Okay, so that radius. And so what if we equate that up to our above equation for AC? And so if this equals big G big M over R squared, now be careful here. One set of R's does not cancel. Let's solve for omega. Before we do the square root, we got to divide both sides by R. What's going to happen? R squared in the denominator with another R in the denominator.
R cubed.
R cubed. So big G big M over R cubed, and then take the square root.
Non-split.
Yeah, if you relate it to rotation. Hopefully our satellite is non-slip condition. Okay, everybody good with those two? Now I'm going to highlight them just because that's our final answers. Do I recommend you memorize them? I don't really recommend a whole lot. Hopefully you know how we got them. Yes? Now I'll tell you probably more often, again, as soon as I say this, knock on wood, I would expect AP to focus more on the orbit speed, just because I've seen most examples that way. Could they ask for orbital angular speed? Sure, it's not of the realm, but you know, if you had to say, I'm only going to memorize one, Ms. Earhart, which one would it be? I would do the first one, okay? That's probably the more common. But they do expect you to derive. And so you still need to know where it came from. Again, a lot of them say derive an expression. That's AP lingo, okay? So know how it comes to be. All right. Little bit same, little bit different. We're going to bring back numbers. Wait, Ms. Earhart, there's no numbers in this problem. I know, but we've got some numbers. A geosynchronous satellite. Geo is leading us to think about what? Earth. Synchronous is leading us to think about it's in sync with Earth, it's timing of Earth. And so what timing of Earth would they be talking about? The time of one rotation, AKA, it's been a while since we've said the P word, period. And so what this means, it has the same period as Earth, okay? And so it's in a spot above Earth, and it's always going to remain in that spot because as the Earth rotates, it rotates exactly in the same timing. By the way, they didn't tell us the timing of one Earth rotation. You know it. One day. Ooh, SI, we don't like days. Yep, but probably next we would say 24 hours, which then we have to convert to seconds. Now, if you want to go through minutes, you can. But how many seconds are in 1 hour? 3,600. And so the period is 24 times 3,600, which is, right. So 86,400 seconds, or 8.64 times 10 to the 4th, either way. So did they give us that number? No, but we know the rotation of Earth, and you got to know geosynchronous. It's in sync with the Earth. All right, and then it says at the same point of the equator of the Earth, determine two things: the height above the Earth's surface, such that this satellite must orbit. Notice, height above Earth's surface, not center, height above the surface. And then what's the speed of that satellite? And so how are we going to do that? We need to keep our derivation going. We just figured out an orbital speed. Can we ... take it in terms of period? And so I'm going to use the v squared version, okay? And so over here, I'm going to say v squared equals gm over r. Okay? I don't know if that's easier. Anyway, what is v equal to in terms of period? The speed of a orbiting satellite. What distance does it travel? What time does it take? Distance would be that circumference. Time would be period. And so if we want to square the velocity, we got to square everybody, okay? So the numerator turns into 4 pi squared r squared over t squared equals gm over r. What are we solving for? Before we solve for the height above the surface, maybe we solve for r and get that center to center separation. So let's put our r's together. Either way we go, you got to multiply both sides by r. So we would get 4 pi squared r cubed. I think this is the only time in the year we do cubed. And then 2 more steps. We want to isolate r. And so multiply both sides by t squared, divide both sides by 4 pi squared, and we get r cubed is gm t squared over, and I'm going to bring that parentheses back. Nope, not the r, 4 pi squared. And then final answer, we got to do what? Cube root. And I think on these calculators, the math button has it as a 4th option there. I don't know. I have to remind myself every year.
F2 and then put any number you want.
Okay. So I'm gonna plug our numbers in. Again, they didn't give us any numbers, but some of these are known. Okay. G is 6.67 times 10 to negative 11. Mass, it's the big mass, and this is satellite and Earth. So we want the mass of the Earth. And so that was the 5.972, I believe, times 10 to the 24th. And then T was that 86,400 seconds. Don't forget to square that one. All over, know your calculator, if it needs the parentheses or not. I think these yellow ones do, okay? So again, this is a whole lot. I don't recommend doing this in one calculator step. I break it down into numerator, denominator, and then I'll cube root. So calculate with me. Times, I know it. So I got, for the numerator, 2.97354. Keep as many decimals as you can stand. And then divided by 4 pi squared. I'll use parentheses. Divided by parentheses 4 times pi squared. And then I'll do cube root and answer. So I get, and y'all, this is R. This is not our final answer. Bear with me, y'all. I think that's 7. That's the center to center distance. They want the height above the Earth's surface. One final step to get that first answer would be, I got to subtract the radius of the Earth, which is that 378 times 10 to the 6th. Okay, and so minus. And so final answer, the height above the Earth is and since it's a final answer, I think it's safe to call it 3.6 times 10 to the 7th meters. Now that we know all this, could we go find the orbital speed? That one's going to be quicker. And so we'll go ahead and do that. Orbital speed, we already derived that as the square root g big M over r, 6.67, 5.972. And then r, it's got to be that total center to center distance. So before we subtracted, so that 4.2232 times 10 to the 7th. And so and square root, I get an orbital speed of 3,071, or probably sig fig 3,070 meters per second. For the satellite to remain in the same place, it needs to be at that distance and that speed. What if it goes too far away? It would have to speed up or slow down if the radius got larger. If you have a bigger denominator, that would be a smaller velocity. I said, what if it gets further? Okay. All right, next class, we're going to talk about potential energy again, but for far range distance, no more MGH.